ಹಿಂಗೆ ಚೂರು ಎಳ್ಕೊಂಡು ಹೋಗೋದು ಬಾಕ್ಲ. Hello, good afternoon.
Good afternoon, sir.
Okay, your bandwidth is relatively weaker. I hope others can join. 2 seconds.
Good afternoon, sir.
Yeah, congratulations for all of you for successful completion of 1 year. Those who joined the first batch on 22nd October last year. Some echo was there. Okay, just I minimized. Okay, let others can join later. Actually, we'll start. I will start sharing the screen. Okay, let it be the same case where we can have the research techniques in atmospheric physics. Or the sir, but I've discussed with you the same technique, not same actually, similar techniques in astrophysics to a great extent. Techniques does not distinguish between either for atmospheric or maybe astro or nano or maybe nuclear or maybe a condensed matter or maybe a material science or any field, maybe even life science doesn't matter actually. Because science is a science actually. Because the extensively the techniques which are used in particular discipline can be recognized. Of course, while giving a topic, we are mentioning in such a way that how these techniques can be used broadly over the science spectrum in the sense, okay, maybe in a narrow way, how that can be used for the research purpose to a great extent. I'll continue. I hope you appreciated the last discussions, whatever we had done in the last class actually. We'll continue the same way. Even though it looks like a basics for you, the understanding of the electromagnetic radiation, but it should not. It should not. Why? Because the kid, whatever they are learning either in fundamentals, starting from standard 1 to 5 was earlier, now they redefined. The NP is redefining them with the standard 1 to 3, or maybe in the middle, or maybe in the higher school, differs. But the same subjects also taught to some extent in the +2 or maybe intermediate, maybe in your graduation and also master graduation. Again, you are coming up with the same similar topics in research. But the understanding has to differ from the level what you started as a fundamental courses, the level what you are thinking of in research to a great extent. In fact, each topic is worth of innumerable number of the research works, particularly that may lead to the PhD or that may lead to the Nobel work, that may lead to the any exaggerating results that can be continuously strived off. There is no doubt. Even though there is no saturation in research in such a way that some field, most of the work has been done. There are no scope for the further extension or further continuation. Usually, sometimes the scientific community will reveal like that, but it is not of that kind. Of course, it depends on certain techniques, certain possibilities, certain instrumentations, certain knowledge. But thing is that instead of spending money or instead of investing money, crores together or maybe billions together, always the governments or by the scientific community encourages the ideas. If you are having a good idea with any of the concepts or topics, actually, certainly that should be fetched in a really considerable way and in a considerable time. We'll see that how that best can be done actually. This is the topic what I shown that in my syllabus what they have done. Okay, last class we discussed mostly the introductory part. Of course, we should not restrict only for us. Today, let us see the same thing. The continuation looks like an introduction, but in a different way. Actually. How they will see that today is enough for me to complete the rest of the part in the topic number 1. As if you recapitulate what we discussed in last class, actually, this is one of the spectrum, particularly either in terms of the wavelength or in terms of frequency or in terms of what actually energy also you can expect. Energy also. And how that spectrum has to move from the left extreme with the long waves to the right extreme with the short waves, or left extreme with the more wavelength in terms of wavelength of the longer wavelength, the right extreme with the shorter wavelength, or in terms of the energy, left extreme with the minimal energy. Relative, it is a relative word actually, and it is not the most, it is utmost energy. Compared to the radiable waves, gamma rays are always having a higher energy. Gamma rays are the one which can penetrate through all kind of a material to a great extent. Of course, that also depends on the so many parameters. Those parameters, if time permits, we will discuss actually. And radio waves, particularly either AM radio wave or FM radio or maybe cell phones or even the what we can call remotes, whatever can handle to operate these signals actually, either maybe TV remote signal or any kind of a remote, doesn't matter. Mostly works with radio waves and microwaves. And the thermal energy, particularly they will go with the infrared. Then ultraviolet is radiation after the visible. Visible is very narrow. Visible is very narrow. Then outwards we'll get the next phase of different mode and the gamma rays. This we discuss. Gamma rays preferably from the nuclear reactions or maybe a reactor or maybe all kind of a stars. Whatever with the kind you can call G1 star to about the G5 star of that kind, a special kind of a classification in astrophysics deals with the different kind of an emission of the radiation they can call. Preferably you name that as the electromagnetic, need not be only in the visible spectrum, in all spectrum of that kind. Okay. Let us see how it works actually. Light was known to be a wave, of course, no doubt, sometimes the particles also. The production and the measurement of these electromagnetic waves of any frequencies which are confirmed that the light was an electromagnetic wave as well. Need not be only in a wave. Light in a sense, usually in a broader sense, or maybe a lighter sense also you can say that, broader and lighter sense by common man, light means only the visible spectra, they will say, not the entire magnetic spectrum. But the production of these electromagnetic waves, what you expect as a wave, falls with the all kind of frequencies starting from 60 hertz of an AC current on the left extreme to a great extent what you can see, almost 10 to the power 20 plus hertz they can call actually, with the gamma goes. Okay, confined to the electromagnetic wave. One can have the relation of this electromagnetic wave, particularly the speed, if it is linked with the frequency, okay, or the wavelength times the frequency of the wave must lead to some constant value. That constant is known as the speed of light in vacuum. Okay, speed of light in vacuum actually. Because this you can see that 7.5 to about almost 4 ions for what you can call 10 to the power minus 7 of a meter, or 0.75 to about 400 0.7.5 for micron of micron, or 750 to 400 nanometer, 7,500 to 4,000 angstrom. Since the spectrum is indicating a reverse order in such a way, okay, the energy is increasing, of course, then if energy is increasing means frequency what happens also has to increase. That is why wavelength has to come down. You are getting from red to the violet. Usually the spectrum will go with wave gaia, violet to the red it has to go. It is a reverse spectrum of that kind. No issue. And radio waves is a broad spectrum. Almost if you expect the wavelength that goes from few meters to almost a few kilometers, few tens of kilometers you can expect. In infrared, maybe micrometer to about micrometers to a small few meters of that kind. In ultraviolet of the order of several nanometers. Okay, and gamma rays certainly femtometer or maybe picometers they can call actually, pico to femtometer of that kind. It's a wide spectrum and is a broad spectrum of that kind. These electromagnetic waves can have any wavelength, no doubt out of it. These electromagnets also have different names to different parts of the spectrum. For example, what I am naming as a radio wave, microwave, infrared, ultraviolet, X-rays, gamma rays, so on and so forth actually. Within these microwaves, they can go with either TV signal, FM, or maybe an AM, or maybe cellular phones and satellite applications, and with the rest of the part. We'll see how best one can ask to do it. Let it be with some kind of a descriptive part in such a way. Electromagnetic energy travels in waves, no doubt, and spans broad spectrum from very long radio wave to a very short gamma rays. What I told earlier, the human eye, means that is our eyes, can only detect a small portion of this spectrum called the visible light. Okay, among the visible, there will be a different perception actually, because all of us can't recognize the same color. Of course, blue may be a blue, no doubt out of it actually. Red may be a red out of it. Green may be a green, but it differs from person to person also while analyzing. But if you are having a digital signal, if you are having a digital detector of that kind, a mechanical detector of that kind, to detect and identify, that should not differ. That should not differ of that kind. Of course, it depends on the calibration factor. It also depends on the material property, metal property. But the same signal strength while detecting the signal strength, can go away in the sense of degrade with the degradation of the sensors. That is a different issue. And you might have heard actually, I don't know whether they met it or not, there are some people with color blindness. They can't see that. Everything looks like only black and white. The baby which was born, newly born babies, always will not recognize the colors. They take some time actually, sometimes maybe a few months to a few years to recognize the colors. Okay, means you should feel lucky to have the distinction between the different colors where the nature has given such a strength for individuals to identify them with the different materials. Assume that if all colors are made up of only blue, okay, where you are sitting in a room or maybe a hostel or maybe a classroom or maybe in the department, just imagine you are, apart from seeing the display either in a laptop or maybe mobile, just to see the surrounding around you actually. If everything is made up of only a single color, either table, chair, materials, pen, paper, walls, lights, everything, you can't distinguish them actually. See, if you put a blue color ball in a ocean, you can't distinguish. If you paint a wall, white color painting wall, if you display something, a display in a white color, you can't distinguish. If there is some blackboard, if you paint that again with the black paint, you can't distinguish. There's a different thing actually. It will happen of that kind. But why I am saying, because in surrounding, if there is no difference in the colors, if you can't identify them, those objects as an individual objects or an independent objects, if you want to see the nature, if you want to see the universe, if you want to see the celestial bodies of different kind, we don't know what they are of actually. If you want to recognize them, if you want to, may not be discovery, if you want to identify them actually, then your detector or the detector, what we want to have, the development of the detector should have all such type of knowledge. Means a radio wave detects, radio means radio waves, detects the different portion of the spectrum, and an X-ray machine uses yet another portion. Means radio waves are certainly different, and left extreme case, and X-rays are of different kind. Sun is also a source of energy, there is no doubt. Across this full spectrum, starting from gamma radiation to the radio waves. Okay, and the electromagnetic radiation bombards the Earth's atmosphere constantly. Sun emits the radiation. If there are no obstacles, it will never stop. Continuously it has to go. Continuously it has to go. It can cross even Neptune, Pluto. Of course, Pluto is not there as one of the actual planets. Okay, it is excluded from 2006 onwards for not obeying the properties of the planets in a celestial system or maybe a solar system of that kind. Means the radiation which is emitted by the sun enters the Earth's atmosphere from the top actually, it interacts with the atmospheric molecules. No doubt. We'll see later if you want to have any great interactions only for the perspective of the interaction of the radiation with any of the constituents, particularly in matter, or maybe the atmosphere to a great extent. However, the Earth's atmosphere also protects, no doubt. It acts like an umbrella us from the exposure to a range of higher energy waves that can be harmful to the life. Not all radiations is harmful. Not all, we can call them as the background radiation, they can call. Background radiation is not a disaster actually. We need it. We want of it actually. For example, if a country or a place, you can, or a region, if we expect actually like a northern pole or maybe southern pole, if the radiation does not allow, does not reaches those points actually, those regions always becomes cooler and cooler, and the temperatures are sub-zeros always. Life must be a difficult task. Okay, means if no atmosphere at all, the radiation, whatever which is coming from the sun, entire flux incidents at the surface of the Earth, where we are having a direct exposure, certainly the life was a miserable in the sense the temperature might have gone up, our skins or our life is not made according to the radiation what it was earlier of that time. Means to say, even like gamma rays, X-rays, some of the ultraviolet waves are ionizing. There is no doubt. What you mean by ionization? Ionization is the case in such a way where high amount of energy and can knock or remove the electrons from the atoms. Means if that is good enough to remove an electron, then atom is not in stable condition. Atom becomes an unstable. Molecules will becomes an unstable because of the unstableness or not having the stability. No existence of matter. Matter means if continuous bombardment, continuous striking off the energy by any kind of a mode, either maybe from thermal or maybe electromagnetic or maybe any kind of a mode actually, if it knocks out, it makes the atoms to be unstable to a great extent. You can't expect the matter should lie of that kind. For example, the life of a in a universe they can call so far is about 4.5 billion years. The Earth is also of the same kind, 4.5 billion years. Being some elements, special elements like radioactive elements, which can decay on its own without having the impact mass or without having the influence of any kind of a kind of interactions from the either nature, from the universe to a great extent. They decay on themselves. Okay, that you can define it by the half-life or whatever the case. Assume that, for example, like an uranium, they say that the half-life of the uranium is about 4.5 billion years right now. They almost the age of the universe. Means to say that assume that if you're having a 1 kilogram sample, it is a huge amount. Huge not in terms of the money, but in terms of the intensity and the radiation. If you're having a 1 kg sample right now in your lab, maybe when the formation of the Earth was occurred, it might be about 2 kg. Means or the total content of the uranium what we are having right now on the planet Earth, maybe inside certainly, okay, either on the surface or maybe very well interior, might have decayed. 50% of it content might have decayed actually. No, sir. There is no surprise because you learned the decay loss to a great extent. Actually, you are well aware of it. Imagine right now, if the half life is about hardly about 1 day, okay, what do you expect actually from last 100 years? You can't expect those species or those elements on the earth. Means if the lifetime is quite less, maybe dinosaurs and other things have extinguished from the earth actually. One may be the lifetime, and another case is that maybe the so many what we can call impacts might have continuously occurred onto the earth, and that might have made them to diminish. The similarities you can expect because Earth is a beautiful planet, beauty in the sense by protecting us, all kind of life and organisms on the Earth. And it also possesses a magnetosphere. Because of that magnetosphere, the highly charged particles, particularly charged and energetic particles, will not enter the Earth and reach the surface. You expect either Mars, you expect either Venus, you expect something other planets actually apart from the Earth, where that doesn't have the magnetic field at all in the sense, or if the existing magnetic field may be feeble, very weak actually, then it allows everything actually. Then if it allows everything means the planet's temperature has to go up, and if the temperature goes up, the existence of the life is unquestionable or challenging. Okay, fine, no problem. Then the next topic goes, next statement goes in such a way that exposure to these kind of high energetic particles, high energetic waves, they can call alter the atoms and the molecules and thereby causing damage to the cells in an organic matter by like an organism, what we are having a life. Okay, either maybe human being or maybe another. Means these changes to the cells can sometimes be helpful to cure, to remove, or to omit the cells, organic cells, as when radiation is used to kill the cancer cells, and in other times or most of the time, it may also get a sunburn, we can call. Background radiation is a good. Background radiation is not a disaster actually. It must have. Background radiation must be there actually. Okay, background radiation is not harmful. If the background radiation crosses some limitation, then only it is a carcinogenic. Even pollutants like carbon dioxide, like methane, like other constituents actually, they are very much required. Okay, if that number goes beyond some limit, then they can say that you can call them as a pollutant. Being this, okay, electromagnetic radiation is reflected, sure, so also are absorbed, and it can't be both to a great extent, or maybe some portion gets reflected, some portion gets absorbed, mainly by several gases in the Earth's atmosphere. For example, most important atmospheric constituents are water vapor, carbon dioxide, and ozone. Don't get surprised. You might have studied from your basic school. Nitrogen, oxygen, argon are the major constituents. Here, these constituents are referred in terms of the interaction of electromagnetic radiation with the matter. Okay, don't get some radiations, for example, maybe like visible light, largely passes through the atmosphere. Means, or it is transmitted. They can call. It is entering from the top of the atmosphere, about 100 kilometer height actually, and it has to pass through the atmosphere and reaches the surface. Means Earth's atmosphere is alloying. Means they can call it as it is a transparent for the visible radiation, but it is an opaque for ultraviolet. Opaque in the sense it does not allow most of the ultraviolet which is coming from the sun, okay, most since the radiation, particular ultraviolet, which is most part of the ultraviolet, gets absorbed or gets struck at the stratosphere heights, mainly by the interaction of that kind of radiation with the ozone molecules, which are relatively in higher concentration compared to the surface. Means these regions, these in the sense of the atmosphere, of the spectrum of the wavelength, visible spectrum of the wavelength that can pass through the atmosphere are referred to as the atmospheric window. You might have seen in the very beginning earlier diagram, here, this is the visible light, what you are expecting. This is the atmospheric window they can call. This is the atmospheric window. Optical window they can call, optical window they referred here actually for this entire kind, including thermal. Some microwaves can even pass through the clouds. There is no doubt. Okay, but the visible radiation between 400 to 800 nanometer may not actually, which makes them best wavelength for transmitting the satellite communication signals. Some of the microwaves, okay, they can pass through the clouds. Otherwise, if there are some obstacles, you can't achieve the communication at all. If you want to achieve the communication where the satellite is put into the orbit at about 400-500 kilometer, maybe the low Earth orbit satellites, or maybe medium Earth orbit satellites, about some 20,000 kilometer communication satellites, can't be under our control, can't be under our what we can call under our monitoring actually. Because if you are unable to get the signals, or if you are unable to send the signals to track or to maintain actually, then the era of the communication was an almost nil, or the satellite communication was there. In the sense, some of the microwaves in particular frequency or maybe a particular wavelength can pass through the clouds to a great extent, which makes them the best wavelength for transmitting the satellite communication or signals. You are having mobiles in your hand right now. You are listening to my talk right now through the internet connectivity. That's mainly because of the interaction of or the making use of the microwaves for communication from one point to the another point. Fine. While the atmosphere is essential to protect the life on Earth, there is no doubt, and also keeping the planet as an habitable planet, it is not very helpful when it comes to the study of sources of high energy radiation in space. If Professor Vijaykumar Dodmani sir is maybe with me right now, he may be arguing in such a way that the atmosphere is a great obstacle for the astronauts, great obstacle for the astronomers, great obstacle for the astrophysicists to study, to understand, to see the eternal world, outer world, or the extraterrestrial world, not on the same studies, not only particularly for the Earth, extraterrestrial world. At the same time, the same atmosphere is also a hindrance for the satellites, maybe during launch, that is due to the friction, or to communicate the signals, and certainly the signals has to pass through this great atmosphere and has to undergo very difficult situations. The problems what you are facing in your PhD program, the electromagnetic radiation also has to face several challenges to communicate to the instruments, to communicate to the devices, to communicate from one point of the source to the target or maybe the detectors of that kind. Instruments which have to be positioned above the Earth's energy absorbing atmosphere to see the world, what kind of a world which is having a higher energy and even some lower energy light sources such as quasars. It's difficult task. Still, one has to understand the great spectrum of the electromagnetic spectrum to analyze or to know the eternal world. Oh my God, this is a topic goes with the anatomy of a cockroach, anatomy of a parrot, anatomy of something else. You might have seen that. Okay, scientists will also have the anatomy of the electromagnetic wave, okay, anatomy of a human being, okay, like that. Means energy, which is a measure of the ability to do work. There's no doubt, which comes in many forms and can transform from one type to another. Means to say that we are defining, we are narrating, we are giving a description of the same electromagnetic wave, what we are referring. It is worth of more than billion PhDs across the world, even though you can't stop understanding any kind of a phenomena, because this is such a vast and indeed a great topic of that kind. Okay, forms and can transform energy from one to the another. There are different ways actually. You can transfer the energy from one point to the other. You can physically transfer the, or you can change the position of an object, physical object, from one point to the another point actually. How? By moving them. If you want to move them, there should be an energy. That energy has to come from different forms. The energy also can be transferred from one point to the one form to the another form actually. For example, if energy is stored in batteries, like either lithium battery or tubular batteries, or maybe in maintenance free batteries, or any kind of a battery. You are wearing your watches, for example, to see the time, or actually you are seeing, you are having your calculators, you are having mobiles, they are running on batteries to a great extent. The lifetime of the batteries starts from few months to about few years actually, to a great extent. And potential energy of the water, maybe behind the dam, for example, unless until there may be an obstruction actually, the energy which is stored, energy gets locked actually. Energy gets locked, that and locked energy will be there forever. Objects are in motion, for example, like a kinetic energy, movement of either train, vehicle, airplane, or whichever you feel. There is no end for the imagination. So you imagine until unless you get the PhD, there is no doubt. Charged particles, for example, like electrons and protons, can create the electromagnetic fields. Remember here, we are going deeper with the statements in such a way. Charged particles like electrons and protons, they means if they move, they can generate, they can create, they can form, they produce the electromagnetic fields when they move. And these fields transport the type of an energy, what we can call them as the electromagnetic radiation, or a common man will call that as the light. Okay, means light is only for the visible to a greater extent. You restrict it, being a PhD scholar. Okay, even as an postdoctoral thing to that kind. But mechanical and electromagnetic waves are two important waves that energy is transported in the world around us. There are no, means either mechanical, whichever may be the mode you expect actually, movement of physical movement of the objects, and the movement of the electromagnetic radiation from one point to the another point are the two kind of the waves actually, there the energy is transported. Waves in water, for example, if you throw a stone, you'll get a pebble, okay, you will have the water waves. You might have seen that, you might have understood in your earlier class, both in graduation and post-graduation actually. And the sound waves in air are the mechanical waves. But these mechanical waves are caused by the disturbances or maybe the vibrations in a matter, whether it may be a solid body or liquid body or gas or maybe plasma. Plasma is also having a waves. But similarly to the electromagnetic radiation, we'll see how. Earlier also, the right bottom panel, you are well aware. Still, I'm showing that electricity can be a static, no doubt. If you have an isolated charge of either negative electron, or maybe a positron, or maybe a proton of that kind, like the energy that can make your hair to stand on it, one end. You see the right top picture. If there is a huge electric field, you might have witnessed it from the books. If you have a good habit of reading the books, either on an hardbound or maybe a soft copy version of that kind, gadgets, from what they can call a Resnick halide Walker. Okay, that is a combined issue or voluminous issue actually. Where they might have put that while studying the electricity and magnetism or electricity alone, if there are static charges put together to a great extent actually, in the earth before the lightning was occurring, lightning was hitting, lightning was about to generate and struck actually, the field generated, that raised field has made her hairs to grow like this, almost like a spikes. Okay, electricity is a static, no problem. Like the energy that can be make your hair to stand on one end like a spikes. Similarly, magnetism also can be a static, as it is in the refrigerator as a magnet, they can call. Or you see the magnetic field here in the middle panel actually, being a magnet, north and south pole on each side actually. If you are going dividing the magnet into an house, it will never lose its property till even you can reach to the extent of the atomic molecule to a great extent. See that these are this almost similar to that of a price. This is one with the electric field. This is the bottom, sorry, middle one is with the magnetic field. The electromagnetic radiation, what you are expecting actually, this is a property of changing the magnetic field will induce the changing electric field, and changing electric field will induce the electromagnetic field, but both are linked together. And it forms the electromagnetic wave. Maybe a component of electric field, maybe I'll assume that vertical red lines actually being a polarized light of that kind. And this is the bottom one with the blue color horizontal lines with the magnetic field. The combined effect shows that it is an electromagnetic wave. The movement are changing, need not be moving. Moving charges will create the current of electrons, they can call, current of the charge carriers, you can call, that produces some field, electric field. The same moving electric field produces the magnetic field, and the variable magnetic field produces the electric field, and the combined effect of them leads to both horizontal and vertical component. Wave has to move from the left to right or in the direction of the propagation of the light, what it is shown on the bottom side of the diagram. Okay. Electromagnetic waves differ from mechanical waves. Don't compare them like what mechanical waves, what we are expecting for the waves over ocean, waves over any kind of a pond, they can call. In a way, they do not require a medium to propagate. Means for the mechanical waves, media is essential, media is a must. Means for electromagnetic wave, they can travel not only through air, not only through the materials, not only through the solids, but also through the vacuum of the space. Okay, you are well aware of it, there is no doubt. Here you are getting one good scientist. Of course, as soon as you hear the name of them, most during the studies we used to walk away, because particularly if there is an viva component either in laboratory or maybe even during the selection process, either for the research career or maybe in opportunities as a scientist or maybe as an academicians or as a faculty. It is a well-known phenomenon to ask the Maxwell's equations. James Clerk Maxwell developed a scientific theory to explain the motion or movement of the electromagnetic waves. Only 4 set of equations actually, either in terms of electric field or magnetic field, how that can lead to the electromagnetic wave. That I'm not touching in this class today. Electrical and magnetic fields can couple together to form the electromagnetic waves, there is no doubt. The senses Clerk Maxwell summarized the relationship between electricity and magnetism into what are now referred to as the Maxwell's equations. Okay? That you read at your free time, no doubt, but you will get a very good knowledge out of it. Based on this, electricity can be static, like the energy that can make your hair stand. I am sure that you will witness this type of a photograph by reading the text. At the same time, I wish that you will have a practical experience also while doing PhD. I will leave to you with the next slide for a minute. If something goes wrong, your hairs will be like a spikes. If you are unable to solve some of the research problems, if you are unable to decode some of the problems, if you are unable to have a good paper in your hand, if you are having something which is not working according to wish and fancy of you, sometimes it may not be in timely manner. Yeah, there's no doubt. In PhD time, certainly all of you, I wish that you be like that. Then only you will get some good results. Then only you will get some good results. You will get good papers. You will get a good work actually. Okay, but let it be at the early stage, not enough. Just to have it. Being this, it is not fine. Is it the electromagnetic waves? What we are referring, is it waves, or can I call it as an electromagnetic particles? Yes, you can call, no doubt, but there should be justification for those. Light is made of discrete packets of energy, which are called photons. Okay, but photons carry momentum. They doesn't have the mass and travel at the speed of the light, about 2.98999 something, so much things you can go. All light, what we are expecting, is all electromagnetic light or electromagnetic spectrum, they can call, has both particle-like nature, and also wave-like properties. If that is the case, what you are expecting, it looks like a simple and repetition what you have heard so far. But go for the fourth statement. How an instrument is designed to sense the light that influence of the light influences which of these properties. For example, if I am having some sensor in my hand, Can it detect the momentum? Can it detect energy? Can it detect the wavelength? Can it detect the frequency? If that is so, what region it has to do? Whether in the visible, whether in ultraviolet, whether in microwave, whether in some kind of a thing, actually, like gamma rays. Maybe among the gamma rays, so many energy, wide spectrum is there actually. I can't. Even our human eye, it is very sensitive only for the visible radiation between 4,000 to about 8,000 angstrom. Any radiation lesser than that, I can't see that. Even though it is visible for a detector, it is not visible for me. Bats are moving. Bats means like a creatures actually. Bats are moving during night time. They can sense their eyes are good. Lions, all lions, snakes, they can move during dark actually. We can't. Being a human being, this is our inability to see the darkness. This is our inability to see the energy spectrum, excluding the visible spectrum. I want to design, then you have to see that an instrument that diffracts the light due to the diffraction phenomena into a spectrum for analysis is observing wave-like property of the light. I hope you got it. Which, if you are having any instrument, any sensors, is the one in such a way where it diffracts the light into the spectrum for analysis, is observing the wave-like pattern, wave-like property of the light. Dispersion is wave-like property. Dispersion, interference is wave-like property, and diffraction, interference, diffraction, and polarization is wave-like property. But what particles we expect? Particle nature of light is also observed by the detectors. There is no doubt it, which are used in the digital cameras. How digital cameras are working? You may be handling your mobiles. They are nothing but the digital cameras, where an individual photon which liberates the electrons or which releases the electrons, those are used to detect and store the image data. For example, due to this property, maybe some may emit more energy, some may emit less energy, and the combined effect can be seen in a better way. That we'll see that actually. Let it be with different descriptions like polarization. One of the physical property of light which is used that can be polarized. Means light, even though it travels in a straight line to allow the rectilinear propagation of light actually, but it is also having a property called the polarization. There are various types of polarizations they can call, either circularly polarized, circularly linearly polarized, elliptically polarized. You have studied and also done some of the experiments actually. If you put a prism like a Nikon prism and maybe with some polarizer, you can see that. In fact, polarization is a measurement of the electromagnetic field's alignment. If they are parallel to the grid, if they are parallel to the lid, if they are parallel to the slit, they can call it halos. Any directions which is not parallel, certainly it gets attenuated. Okay? Means thereby reducing the intensity to reach the detector. Fine. Oh, sorry, in the figure above, I mentioned the electric field are in red and is vertically polarized. I will go back to the previous slide. Here, electric field are vertically polarized, and these are magnetic fields are horizontally polarized. If you keep a state with vertical state, certainly rays will pass through. If you keep anything horizontal, it will pass through. But if it is a combined effect, certainly only one is allowed. But I expected the Lloyd's mirror they can call. That is also through the polarization. In one of the orientation, it will pass through. In another, it will be rejected. Okay? Where you can have the dark and bright spectrum, mainly because of this type of a phenomena. This is similar to how sunglasses are able to eliminate the glaring by absorbing the polarized portion of the light. Of course, those who are wearing the spectacles, including me, always prefer that actually we will have some glaring. Anti-glaring glasses they can call. Okay, anti-glaring they will put in such a way to eliminate the intensity or the brightness that reaches the retina of our eye. Even while driving night time, actually, if you are seeing the vehicles which are coming head on, you can't see the path. To minimize that, normally we will wear the sun glaring glasses of that kind. Okay, anti-glaring glasses also there. Being is how that electromagnetic radiations can describe, how that descriptions can go beyond, still further and deeper actually. Light need not be visible light of that kind. Electromagnetic waves and radiation all refers to the same physical phenomena of the electromagnetic energy. We started with electromagnetic spectrum, then all the waves which are refers to some physical phenomenon is known as the electromagnetic energy. And this electromagnetic energy can be described either by frequency or by wavelength or by energy or combination of them. Combination of them in the sense frequency and energy are linked, wavelength and energy are linked, frequency and wavelength are linked, energy, okay, these combinations have been called. Okay, of course, frequency multiplied by its wavelength leads to some constant value. E is equal to h times nu, E is hc by lambda, E is equal to, as a being wave, E is equal to dual de Broglie wavelength. You might have heard that de Broglie wavelength is equal to lambda by 2 pi, what we are expecting. And these are all means all the three phenomena, all these three only are related mathematically. If you know one, at least you can calculate the other two. If you know one, if you know frequency, you can estimate the wavelength and the energy. If you know wavelength, you can estimate either the two. Okay. If you know two, there is no way, there is only an interlink or interlink. Means to say that radio waves and microwaves are described in terms of frequency, no doubt. And the unit normally they will go with cycles per second or hertz. Infrared and visible lights are in terms of meter, that is in terms of the length. X-rays and gamma rays are in terms of the energy. I don't know whether you got it or not. Now you link in such a way what I told. Radio and microwaves in terms of the frequency we are classifying. Infrared and visible light we are classifying in terms of the wavelength, and X-rays in terms of the energy. Okay, means all are interlinked. There is no, this is one classification I am giving actually. Whether in your earlier classes you might have heard of it or not. If you know that, you have to enjoy, no doubt. See that the beauty of human being is that we are capable of understanding the phenomena where other animals can't have it actually. Of course, always it should not be misleaded, it should go in a proper way. Means radio waves and microwaves are described or maybe will be used in terms of the frequency actually. That is one spectrum is in terms of frequency, and infrared visible in terms of the wavelength, and X-rays, gamma rays in terms of the energy. Can't we have the X-rays and gamma rays in frequency? Sure, there is no doubt. We can do it, but we'll never make it. We'll say that highly energetic particles are coming from the sun of the order of a million electron volt to giga electron volt to tera electron volt of that kind. Can we say that visible light that is in the range of about a few electron volt? Of course, you can convert it, but we will say that 4,000 angstrom to about 8,000 angstrom. But if you work out with the radio and microwave, actually, nobody will say that. They will say that how much hertz. For example, FM radio is having a wave frequency of about 93 megahertz. 93 megahertz or about 100 megahertz, that kind. While dealing with this mega is 10 to the power of 6. Million is also 10 to the power of 6. Don't get confusion. Numbers are the same. Numerals are the same. But you are a great physicist. You should understand that when you have to use the mega, when you have to use the million. I can't say that the area of Bangalore is 1 million kilometer. 1 million square kilometer, I can say that. I can't say that it is an 1 megahertz. While referring to the frequency, you might have heard that megahertz. For example, if I count a sheep, if I count 10 bullock carts, if I count the parrots, if I count some items actually, I can't say that even though it is in terms of the 10 to the power of 6, I can't say that it is a mega. It should be million. City is a mega city. It is a continuous. It is a without a break, without a discreteness they can call. Both are countable. There is no doubt. Current should be mega ampere, million ampere current they can call, because 1 ampere is 1 unit of that kind. Megahertz is the frequency. If it comes with the counting, then you go with the million number, like million, billion, trillion of that kind. Population of an India may be billion. Populations of some of the cities are like millions together. Fine. This is a scientific convention that allows and use us to the convenient use of units between the hertz or maybe meter or maybe to the electron volts of that kind, that have numbers that are neither too small or neither too large. We can go, if it is an electron volt, if it is very too small, you can go with million electron volt or giga electron volt or pico electron, of course, penta electron volts of that kind, positive way. You can't go with micro electron volt. You can't go with nano electron volt. Have you heard at any time actually? Maybe scale wise, distance wise, starting from angstrom for an atom, angstrom to a nanometer to about micron, and to a millimeter to a centimeter to the meter, to the extent of about kilometer, maybe an gigameter, of course, tens of thousands of kilometers, till to the extent of picometer. PC, parsec they can call, the distance between sun and earth of that kind, astronomical unit to the astronomical unit to that kind. In terms of the frequency, it can go from any smaller dimension to pico to of the order of the great waves to a great extent. Take this. Good. Good. I'm not giving you anything extra, but whatever you have heard so far. But thing is that at the end of the last minute of this class, you should understand that I have not understood electromagnetism well in the earlier classes. There are chances, there is a scope, there is a way, there are way, not one way. There are the ways to still continue our studies in understanding the behavior, in understanding the properties of the electromagnetic radiation to a great extent. Left top corner shows that it is a simple representation of the frequency and wavelength, how they can differ. Okay, maybe looks like a sinusoidal wave. Why can't we have this sawtooth wave? Why can't we have the rectangular wave? Why can't we have the some other wave, square waves? But electromagnetic radiation normally will represent in terms of the sinusoid. Why can't we just think be an answer for your own sake at least? Okay, if you search, you will get, but at least that should convince you in such a way that why it should not be. For example, if you are using the signals in electronics lab, actually you can have all kind of signals. Okay, frequency generators, you can have three mode, either square wave or maybe rectangular mode or maybe in sawtooth or even sometimes sinusoidal. Sorry, not sometimes, most of the time sinusoidal, rest of them other waves of that kind. Means between the two peaks, whatever way the time taken for to complete one rotation or one cycle they can call, that timer is known as the 1 second per unit. It can call cycles per second is the one wavelength. One wavelength they can call either from crest to crest or trough to trough or anywhere. You start from here and end at this point. You start from here and end at this point. You start from somewhere here, you end at this point. It has to complete 360 degree to complete one cycle of that kind. That is the length. Length of one wave is nothing but how long it will take. How long it will take, how long only, how long not in terms of the time, how much distance it has to take actually. How long it will take time, that is known as the frequency. So many oscillations per second, so many oscillations per unit time is known as the frequency. As you know, as the frequency increases, the number of oscillations will increase. As the frequency increases, wavelength decreases, and as the frequency increases, energy increases. See the bottom panel, bottom right actually. If you are able to have more number of waves, you are having more energy. If you are having less number of waves, for example, if you are having a wire or if you are having a thread actually, two of you, if you vibrate actually, if you get so many vibrations between you, not number of vibrations, okay, number of vibrations between the unit distance they can call. Okay, if the vibrations are more, certainly frequency should be more. If the vibrations between you are less, maybe the energy is less. This is the same concept they can use either for tuning fork or maybe rest of the part of it. Some classifications will come. Maybe it is a reflection, refraction, that kind. I don't want to go in detail because you can read this to a great extent. The left top corner, you can see that actually a packet which is coming here, going back. This is the arrow we can show that. Nobody says that whether it is a particle, whether it is a wave of that kind. Something is hitting will also bounce back. That you can call it as a bounce. But thing is that if you draw a normal to this horizontal line, the angle in which it incidents, the angle in which it goes back is known as the angle of incidence, maybe the angle of reflection, but within the same media. If the energy which is coming in, packet of energy, goes back to the same media, you say that light rays are coming and going back. Instead of that, it says that in such a way that the energy which is coming in has to go back. Few portion of the energy is going back. Remember, actually, that is the reflection part. Means when a light wave encounters an object of any kind, they are either transmitted, no doubt, or maybe a reflected, fine, or maybe an absorbed within the media, or maybe refracted, entered into another media, or maybe polarized, maybe attaining a singularity or singular direction, or maybe diffracted when they encounter certain sharp edge objects, or maybe a scattered. Oh my God, so many are there. Means it's not worried that actually see that maybe they are either transmitted, reflected, absorbed, refracted, polarized, diffracted, or scattered. This depends on the composition of the object. Whether composition in the sense whether it is an iron, whether it is a nickel, whether it is an aluminium, whether it is a mixture of all, whether it is a water molecule, whether it is an ozone molecule, whether it is an helium, whether it is a neon. Okay, and also the wavelength of the light which is emitted. whether in the visible or maybe in microwave, whether in the refracted waves of that kind. Very complicated. Reflection is not a phenomena, but thanks to our teachers, they have convinced us in such a way from the high school. We know that actually, if light falls on an object, it gets reflected back. No doubt. We understood, we accepted the concept without understanding all these phenomena, whether it depends on so many parameters or so many properties of that kind. No doubt. Fine. Okay. With that knowledge, what we gain from our school days, okay, specialized instruments collect the data, collect the information, either in terms of the reflectance, absorptance, reflectivity, polarization, diffraction, or in terms of whatever that we can call data on how electromagnetic waves behave when they interact with matter. Somebody is harsh, somebody is cool, somebody is straightforward, somebody is an angry, somebody is a smile. These are the reflections. These are the behaviors. By seeing the behavior, you can see that actually, whether I have to interact with my own guide or not, whether I can meet the chairperson or not today, whether it is in right time for us to get it done by our work actually. Okay, that's decided by the behaviors. Similarly, electromagnetic wave also interacts with them. Actually, these electromagnetic waves, how they behave with the matter, how they interact with the matter, depends on its energy, depends on its wavelength, depends on its frequency. At the same time, it also depends on the properties of the material, whether it is a hard material, it is a soft material, it is a liquid form, solid form, gaseous form, or mixture of all those things. Whether it is an FCC or BCC or maybe condensed matter staff and researchers and scientists will say with the structure of the atom to a great extent how they can interact actually. Okay, whether it is a radioactive material, non-radioactive material, whether it is a highly energetic particle or non-energetic particle of that kind. See, the concentrate on the middle panel here. Reflection. Fine. When it hits a surface, you'll get the image, no doubt. If you stand in front of a wall, can you see your own image? Don't get confusion with the shadow of your dimension. Can you see your own image? Can you see the hands? Can you see your face? Can you see the dark spots on your face? Can you see the brightness of your face? If you stand before a wall, don't try right now. Wait till the end of the class. Okay. If you see, good. Then mirrors are not required. What specialty is there? Mirror is a certain kind of a glass material. Okay, for window panes also we have put the glass material, but you can see that the intensity of the light is entering into your room. Okay, glass tubes, for example, like tube lights, that is also made up of a glass. Okay, it allows the radiation to pass through. It is not obstructing. Okay, what is the problem with the walls? What is the problem with the table? What is the problem with the piece of a paper? Why it does not allow the radiation to pass through? The same electromagnetic radiation, maybe same radiation in the visible format actually. Okay, you can't. That you has to see. Reflection is when incident light or maybe an incoming light hits an object and bounces off. Here, hits and bounces off. If you are getting more bounce, it's a good reflector. Okay, very smooth surfaces. Smooth, you can make them into the smooth surfaces, such as the mirrors, reflect almost all incident light. If it reflects everything, what will happen? Energy, whatever it is hit in the mirror, will come back. Will come back actually. See that here, mirror image you are expecting for water, even in the liquid form, did not be mirror alone actually, reflects the image. If the water is turbid, if the water is having wavy nature of this kind, you can't see the shadow. Okay, it is an image, you can't see the shadow. By seeing this, your own image, by seeing the received packet of the electromagnetic radiation, the physical and chemical composition of matter determines which wavelength is reflected. Physical and chemical composition of matter determines which wavelength is reflected or which color is reflected. We'll go to the next slide to have a surprise for you. My God, see, this is not the photography of your classmates or friends. This is a photography of our neighbor celestial body, Moon. Hardly it is at a distance of about 4 million kilometers, sorry, 4 lakh kilometers, not 4, about 3.86 lakh kilometers, or okay, whatever you conversion you can have it actually. What you are saying that, so far you never thought that actually Moon will be like this. Maybe some of them, those who are curious, may be interested in space, interested in the astronauts, interested in the planetary science, interested in the nature, might have seen with the images released by any of the space agencies, either from the ISRO or from NASA or from ESA or from any of the space agencies of that kind. Here, what it says that a color gradient, a spectrum, you can say that actually. Forget about the lines in between; they are equidistant, starting from the blue or maybe violet to a great extent to the red and white wave. Means here you can see this the entire globe need not be referred for the Earth. Globe can be referred for any of the spherical objects of that kind. This is for the moon to a great extent. At the center, it is a polar region actually, preferably is a blue in color, and if you go peripheral or outward, radially outward. Somewhere on the top, the reddish in color, somewhere at the bottom, green, yellow, mixture of all the colors. What it says that it is the topography of the moon. Fine, you can have the topography of the sun, Earth also. If you take the topography of the sun, everything becomes white actually. There is no, because the sun is a black body radiator. Sun is the source of the energy. Moon is not of that kind. Moon is the one where it reflects the energy, whatever it is received from the sun, actually it reflects back. By observing that reflection, one can say that what it is composed of. It's a good technology. You send the beam of the light, you just hold a torch, allow the torch to switch on the torch, you send the flash of light will fall on wall, flash of light will fall on any of the obstacles like a table or maybe like a matter, whatever you are having in your room actually. By seeing those flashes, you have to say that what it is made up of, how it is made up of. Okay, what it says, the reflectivity behavior of light is used by the lasers on board any of the missions. Lunar Reconnaissance Orbiter is one as the LRO, they can call science mission satellite, to map the surface of the moon. My God, we know the mountains, we know the valleys, we know the terrain areas, either agricultural land or non-agricultural land. We know the forest, among the forest, wet forest, dry forest, or maybe in non-thing, or maybe ocean or land. Similarly, we want to see that what it is made up of. How it is made up of, what is the terrain behavior, what are the terrain features. You send the one laser beam on board where it revolves, actually, it takes the pictures of topic. Those pictures, composite pictures, if they are bringing them together, it reveals that. Red color flashes are showing that, and blue colors are showing the mountains of that kind. Longer response, of course, if it takes quite long to go and come back, it is further away. It comes very faster, it is nearby. For example, light travels at a speed of 3 million kilometers, they can call 3 lakh kilometers, they can call 3 lakh kilometers. If you get the signal in 2 seconds for going 3 lakh kilometers, coming back another 3 lakh kilometers, 6 lakh, 2 seconds is enough actually. We can say that the object is at a distance of 3 lakh kilometers. If it takes 2 seconds, if it takes 4 seconds, it should be double the distance. If it takes hardly 1 second, half of the distance, they can call equal to that of the C by 2 or 2C or maybe 4C of that kind. Longer response time shows they are farther away the surface and they are having a lower elevation. Means they are not mountains of that kind. Low valleys, deeper valleys. A shorter response time means the surface is closer to the source. What we are sending the signal are having higher elevations like mountains. Lower elevations are shown as purple and blue. See that this is a purple and blue lower elevations, deep valleys, and high elevations are shown in red and brown. This is how that the spectrum. This is done by what we can call this is done by the image with the electromagnetic spectrum of that kind. Few slides. Similarly, it can have an electromagnetic spectrum where it can absorb the light. Absorption occurs when photons from incident light hit the atoms and molecules. Objects, molecules move and vibrate if it is hotter with the energy. This heat is then emitted from an object as thermal energy. Some objects are dark in color, like what I told, dark blue, dark green, dark red, which absorbs the more energy. Black pavements absorb most visible. Light colored concrete sidewalks reflects more energy than it absorbs. And also the black pavement is hotter than the sidewalk because it is a summer days. Photons bounce around during this absorption process and lose bits of energy to the numerous molecules along the surface. Means the thermal energy is the one that radiates in the form of a longer wavelength or infrared. Being this, See the images. The left top is the image of Bangalore taken from the satellite along with the temperature. Bluish color shows that warm, greenish color shows less warm. Means all cities are at second island for the heat. Heat island second call, like mountains, they are heat islands. Right side you see that LULP is that land use and land coverage map, Bangalore urban district between 1989 to about 2001 with a gap of 20 years. See that earlier the Bangalore was like this, 1989. Now this urbanization, it has converted from the rural to the urbanization. See that most of the point. See right now in 2005, my God, see if you say that most of the agricultural activity has stopped, except Lalbagh, not agriculture, greeneries are not there actually. At the same time, while expecting this thing, for your surprise, if you see you might have heard the Ramayana with the Ramasetu, whether true or false is a different issue. If you take the image between Sri Lanka and the India, peninsular India, hardly a distance of about 30 kilometers. This is the landmass. This is the underneath some connectivity exists that they can call Setu or a bridge between India and the Sri Lanka to connect the Nepal. Okay. Here you can see that there is another view. Okay. How that can be seen. Here see that. And that this one is the mountain Himalaya with the cooler temperatures goes at the peaker values and the rest of the part. This is another image.
Hello, sir.
0.5 meter. 1 minute. Last minute. Okay. This is a picture of the Himalaya to a great extent, Mount Everest, Himalaya, with a resolution of about 0.5 meters. This is also in satellite image. One can have signatures like through the diffraction mode. In such a way, light also diffracts whenever it encounters a sharp objects. See these vectors. It gives us the signatures. These signatures can be identified. These signatures can be noted down. Okay. By this kind of a signatures, one can identify the universe. Means signatures vary from person to a person, no doubt. Signatures also vary from object to an object, depending on their material property. This is the last slide with the scattering. Light scatters whenever it encounters a media of an object with the different refractive index. Okay, with the scattering, one can study several things. In the atmosphere, because of the existence of the dust particles of various size, even during volcanic eruptions, which has happened actually, the manures were put into the atmosphere. Those can be identified. You can see the signatures. These are the pictures of the clouds through the scattering phenomena. This is the pictures of the clouds through the scattering phenomena, whether rain-bearing clouds or other clouds of that kind. This is the volcanic plume. Means aerosols they can call by some special terminology. So these are nothing but suspended particulate matter. It can scatter through the clouds. Okay, this is the image captured by the satellites. The last one with the refraction, no doubt, you are well aware. I will not touch upon this. It will go through the reflections. You can have a different phenomena. 1 second. See that the left side phenomena shows for the Saturn, the bottom either red, blue, green. In terms of the wavelength, you can classify. This is the false color composite they can call. It will not happen because our eyes identifies these colors. They are taken like this. Otherwise, the actual spectrum is either in terms of red, blue, green. You can analyze this, the entire thing, either maybe in the visible or infrared on the top, or maybe the X-rays for the galaxy. The bottom panel shows here actually, this is for the temperature variation over the entire globe. This is for the salinity of the water inside the ocean. All these things can be done through the electromagnetic studies. I will stop here, and if you are having any comments, you can post or you can raise later. We will meet next week. Thank you, Nandal. I hope maybe other faculty may be waiting. Let us see. Thank you, Nandal. I will end this slide right now. See you later.